but it still seems to work, guys. Hey guys, welcome back at K's New Space. In the last episode we have worked on this little program here. It makes any rocket hover, or more precisely, it makes the rocket chase a certain desired speed. And we can increase this desired speed by pressing plus. Now to 0, and of course chasing the speed of 0 makes it hover as a happy accident, so to speak. Now make it back land. Now the goal of this video is to essentially write a function that changes the desired speed in a way to make the rocket land without crashing, hopefully. Now first a quick summary of what we've done so far. This is our main loop. In here we do the flight computer calculations, then print some data on the screen, check if we have pressed some keys, and of course lastly sleep data.dt. And data is defined on the very top. This is the class or object that stores all the data, or all the values we're going to change using the flight computer, which is defined below. This is the object that stores all the functions. And there are only two so far. The important one is update. This runs every loop to calculate all the values. This is where the magic happens. So this part is the most important to understand. We begin with the only data point we get from KSP, the current altitude, using this telemetry object which we have received from connecting to KSP. Telemetry. We can check our k.py file where I've written a custom function to connect to KSP. This is the kRPC module which you have to install first, of course. And we get the objects vessel, controller and telemetry, which we of course return. And they get stored in these values here. So again, the current altitude is the only data point we have. The rest is calculated. And that is the current speed using the current altitude minus the last altitude divided by data.dt. And data.dt again is the time we spent inside the loop. And this is the difference in altitude we achieved. So as written here, the speed is the distance over time in meters per second. The same is true for the acceleration. We calculate the current acceleration by dividing the current speed minus the last speed of the last loop we ran. And of course, these last values we store in here at the very bottom, at the end. Now I know this can seem a little confusing if you're not used to it, but just remember, the change in distance over time is the speed, and the change in speed over time is the acceleration. It kind of makes sense, I think. So these are the main values we now work with. First, I calculate a difference in speed, a difference between the desired speed and the current speed. And I use this difference in speed to calculate a difference in acceleration. And for that we have the desired acceleration function, which looks a little ugly, but that's how it is right now. The difference in speed is how close we are to the desired speed. So the closer we get to the desired speed, the lower the acceleration becomes. And the acceleration, of course, is what we control with our throttle. So I return the acceleration and again calculate the difference in acceleration based on this and the current one. So let's say I want to have an acceleration of 10, but I currently only have 5. So this value will be positive. Positive 5, which is of course larger than 0. And this will make the throttle go up, as long as it is of course below point some value which I think should be 89. So the throttle will increase as long as the difference in acceleration is positive. And then, once it flips negative, it will again reduce it. And this here should be 0.2. That's all there is to it. The throttle will go up and down and make the difference in acceleration stay around 0. We can test it again to check how it works live. Here we go. I increase the 10. Zero again. Or maybe here you can see it maybe a little better, the throttle. Pretty neat actually. Let's land again. Okay, important to know is we only control the throttle so far. The rest is done manually. What I want to do first is to get rid of this rather ugly function. It gets the job done, but it's kind of hard to understand, I think. So let me just... I think we can just remove all of it. And it's gone. So what I want to do now is to actually replace all this with a simple mathematical function. And in order to do this, I will use a good old tool called Desmos. Some of you may know it. It's a function plotter. What you can do is you can write a function. Let's call a simple one. F of x equals x. And it will simply plot it out. I've already named the x's here. Epsilon is acceleration and our x is our difference in speed. This is the value we plug into our function. This is the f of x here. Let me make that more clear. So what we had before was a step function. Maybe I will draw it on screen here. We essentially changed the desired acceleration each time we reached a certain threshold, step by step. And such a step function can be simply replaced by a linear function like f of x equals x. So let's just do it. That's all it is. Our ds is the x, and desired acceleration is the function f of x. Now let's just try how that works. Maybe it's that simple. Okay, nothing exploded. So all this complexity, and it was that simple to replace it. However, it's not perfect yet, because as ds increases, the acceleration increases as well, infinitely so. And of course, I want to put a cap on it. A cap that looks like, let's say g of x equals, let's say 50. So 50 acceleration, 50 meters per second squared, which would be 5 g's. So from 0 to a 50 ds, I want to use this function, and beyond it, simply a static value, like 50. And for that, I will use a simple if again. So if ds is smaller or equal to 50, return ds. Wait, and this is of course, oops. This is our f of x equals x, and else I want to return 50. Let's try it again. Oh no, wait, it works. Not sure why it didn't work before. And now let's go down. works. Now of course, if we check this function again, we have a little problem because we don't really handle negative values, so the limiter only works for the positive ones. So we have to do the same for the negative values and add a minus 50. Add minus 50. Let's do that as well. So in here, and ds larger or equal 0, minus 50 I mean, do this, else return 50 or minus 50, depending on whether ds is positive or negative. So do this, else do this. I think that should work. Test it again. I'll have to go really fast this time in order to test it. Or really high actually, because I want to surpass the threshold of 50. So of course, it's quite hard to get below 50 desired speed. I think I'll just trust it. Trust the math, guys. So what I did now is what I actually want my landing computer to do. Whoops. We have to refuel anyways. There we are again. And let me just comment this here to make this clear. Right now the 50 is a magic value, so I'll add a max acceleration in here. So now this value is of course not the same, because we actually found it out by checking the intersection here. It's just a coincidence because our function is relatively simple, just x. But if we, for example, change it to 2x down the road, this would change, okay? So now it's at 25. So this is the intersection where these functions have the same value, f of x and g of x. So let me type that in here too, where f of x equals g of x. I hope that's not too confusing. Point is, this is all we do. Between minus 50 and 50 ds, we use this function to calculate the desired acceleration. And beyond those max values, we simply use 50 or minus 50. That shall do it for now. We might tweak it later. In particular, I think a little smoother function would work better, but that's only speculation right now. Now, before we go on with the actual landing computer, I want to add one more thing, and that is to drop the throttle to 0 once I exit the program, because that has annoyed me a little. Now it should work. Yup. Okay, finally we can start to develop the landing computer. The first thing is to define a button again, which will initiate the landing. And that goes elif, key pressed. And I will use a pretty safe key that I know doesn't do anything else, which is the German Ö. And of course, keys delay equals 0. And in here I will set a new variable to true, which I first have to define up here. And I will call it please land. It is initialized with false, of course. And down here, please data dot please land equals true. So now I will use this in here. If data dot please land, and because it is a Boolean type, which means true or false, I don't have to type true or something. That is automatic. So if we want to land, I have to do something. Calculate and for that I will write a new function. I will simply call it land speed. And that new function I will use in here. And of course, the land speed will return a value which is my desired speed. So like this. If data please land, then desired speed equals flight comp dot land speed, and this is that function. And land speed, the function also needs an input parameter, which is simply data. Okay, in data we have the current altitude, I think, yes, and that's all we need because the desired altitude is always 0 when landing. So what we do now is pretty much the same we do in our desired acceleration function. We want the desired speed to be big if the altitude is high, and we want it to be low when it is close to 0. And for that I will use my trusty tool again, Desmos, in order to get some clues what kind of a function we need this time. I think it will be an x again, but if you imagine at 400 meters of altitude, we would have 400 meters a second of desired speed. At 10 meters of altitude, 10 meters a second. I think that's a little too much. So what I will do is divide it by, let's say 2. That would mean at 10 altitude only 5 meters per second. And of course we need a limiter again, because we don't want to get too fast. Okay, so return data dot divided by 2, but only oh wait, let me calculate this in advance. So some value speed is equal to data dot divided by 2 Now if speed, wait, we actually need negative speed, of course. So if speed is smaller than, let's say, 100, oh no, it's bigger than 100, or else. So what this means, again, I will type, this is our f of x divided by 2 minus, actually. So we had an error in our Desmos file. We need a negative hit here too. Oops. Of course, the speed has to be negative in order to land. Okay. Now, as long as the speed is bigger than negative 100, use the function. Otherwise, cap it at minus 100. And of course, the function will return speeds like this. Okay, that should work. It's a little less complicated than this one because we of course only have to deal with positive altitudes. We will never drop below 0. Hopefully. The Kraken says otherwise. Anyways, so now that we have our land speed, I think we can give it a go. Why not? Let's try it. No error is always good. Let's go up a little. And now let's land. Okay, I pressed Ö, but nothing happens. Let me slow down again. What is going on here? Ö. Nope. Did I forget something, guys? If data dot please land equals true. I think I need a little message for debugging to check if it actually works here. Let me print out a little value here, why not? Landing. Okay, that works. Ooh. Okay, that worked. So we get in here. Speed. I wrote it for short in order to save some screen space. Now it should work. It's always simple errors like this, guys. Let's try it again. Speed up to 10 meters a second. I think I also need a button to drop my desired speed to 0 because that's a little annoying. But anyways, let's try to land. Okay. Oh. Okay. That was a little too fast, guys. I think we have to tweak our formula a little. Let me see what's going on here. At 40 meters, I am at minus 20. So I think we just have to decrease it a little further. Divided by 4. Now let me do 4.0 just to be sure. Don't really need that, but for me it's a little comforting knowing what kind of types I have. And this is of course a floating value and not an integer. Let's try it again. I think this comes down to trial and error again, so maybe I will skip it, but let's see. It's usually a little harder the further up you go, so I don't want to start too close to the ground. Now, moment of truth. Whoa. Okay. What's happening now? Okay. We bounced off the ground, guys. Oh. Okay, we landed, but it still wasn't as nice as I wanted to be. So let's even go one further. Minus divided by 5. And also try the cap out. Let's go a little higher. So the desired speed should never drop below 100. Although I think 100 is a little excessive here. Anyways. And... Okay, I think we're not high enough yet. Ah, we're too fast. Okay, let's give it one more try, but now divided by 10, just to be sure it's absolutely not too much again. And landing. Almost minus 100. Oh god, I hope this is stable enough with those wings on the bottom. Oh, we're a little too fast, but... Oh, what's now? Okay, it looks good up top, but it's just a little too slow on the bottom. Reminds me of Blue Origin. Not efficient, but it works. So what I want to do now is to change this function into something smoother, closer to the ground. So if data.currentAlt is smaller than 50, do something, else use that one. And because we changed this inside the if, we have to define it beforehand or initialize it. Otherwise, of course, its scope would end behind the else, and this would not exist. Okay, and here we now use a different function, and that function we have to figure out now. Essentially below 50 meters. I want something that looks like this, guys. So I want to keep the acceleration higher or lower, and then drop it more drastically. And if you see this cursor movement here, you might suspect what we're going to use, and that's a logarithm, a log function. Wait, actually a negative logarithm. And we will simply tweak some values now until it looks right. 5, 10. Okay, this looks nice. I've done this before, so I think it shouldn't take too long. Yeah, almost. Oh wait, of course. We have to also shift it to the left a little. I don't want to drop the desired speed to 0, but keep it like, keep some minimum value so we actually land. And minus 0.5 looks actually quite good. So now let's just use this, guys. So in essence, when we drop below 57 meters, we want to switch to this one here. That's because Of course they intersect here at 57, so it doesn't jump suddenly. But we could also use 50. I think it should also work. Anyways, 57, and then copy and paste this function over here. I don't know what, I keep 50 because it looks nicer. Now -7 times plus 06, and of course I have to mention figured out using Desmos. Like so. Because now of course these are all magic numbers, so that we remember where we got them from. So again guys, if our current altitude now drops below 50, we will use this function to calculate the speed, the desired speed. Otherwise we will simply use a linear function like this. Okay, this should hopefully work. Let's try it. No errors. Let's try to go high enough to reach our -100 threshold. We could actually check. We will reach -100 at 420 of altitude. We should. Oh wait, no. We actually changed our function to divide it by 10. I should have taken that into account. Okay, I have to redo this, I think. So that's new. We caught an error before it happened because I forgot to change this function. I did this wrong here. Okay. Now I need to shift this up more. And this is done using this value. +5. Okay. And now more to the left. 8. Up again a little. Okay, this looks good. Although maybe a little sharper. Okay, this looks good now. We intersect at 50 and have a much cleaner drop off. Okay, now copy and paste the new values, which are -3 plus 1.5 and 0. Okay. Let's test it again. Go up. A lot of tweaking today, guys. Okay, now go really far up. We can actually check again where we should reach our threshold at 1300 roundabout. Okay, 2 and 3 as predicted, and it stays at -100. That's our current max desired negative speed. And we're getting some instability, but the computer saved it. Uh-oh. I make use of this log function, but I haven't even imported this log function yet because it's a standard function, but it needs to be imported. So, and the library or the module is called math. And from math I want to import log. That's all. Now it should work. Now let's test it on low altitudes first. Yes, it works. Oh, but -7 is actually quite a lot. Why is it so high? -5, why? Ah, yes. Our rocket has a height and we don't take this into account at all right now. So let me also fix that by hard coding a rocket height equals 6 meters. Hard coded is actually bad, so maybe we can figure it out later how to use some KRPC function to figure that out. But let's keep it hard coded for now. And we will use this value to add to our current altitude. Plus data dot like so. Oh wait, not here. You know what? Let me define an x. And that x is data dot. This is much more readable. Okay. This is now simply x. Should have done that from the start. Okay, I'll keep that for readability. And now all I need to do is add it here, I think. Let's test it again. Let's land. Nope. I think I have to subtract it instead. Yes, because without it, our vehicle thinks it's 6 meters higher than it actually is. So when it reaches 6 meters, I want it to think that it's at 0. So, of course, I have to subtract it. I should really think before I do, but sometimes I'm just too quick. Okay, let's try it. Hopefully one last time. Land. Oh no. We got a math domain error. Let's check what it means. I think it has to do with the logarithm not being defined much past 0, so I really want to make sure that it doesn't use the logarithm for negative values. So I think what the issue is, our x can become negative for a short moment before touchdown, so I want to make sure not to use negative values. Let's see. If x is smaller than 0, oh wait, if x is larger or equal to 0, do this, else, so if for some reason the altitude is smaller than 0, I want to just return 0 for our desired speed. This is like the minimum value. Okay, a little messy, but let's try. And land. Okay, it touches down and then drops to 0 and then stops. Why does it stop and stays at 0? Let's try it again. Bit confused here. And land. Okay, this works. It's a little high, I think, but it's okay. Our desired speed. Ah, okay. We're at 7. I think the rocket height is simply too large. I'm not sure what the internal value is. Let's try with a lower value. Yeah, this works better, but I think even that is too high. This might have to do with our function, but I'm not entirely sure why it wants me to pick lower values for our rocket height, but let's just go with it. And land. I think we're a little too fast. Okay, so the moment we touch down, I actually want, so when this becomes 0, I want data.pleaseLand to turn to false, because we of course landed already. And I think we also have to tweak our values a little more, because the... Okay guys, this has gotten a little too confusing, so let me rewrite this whole thing here. Now what I wanted to do is use this function from 0 to 30. Below 0, keep it at 0, and above 30, turn it into our minus x divided by 10 function. Okay, so we need 3 cases. First, if x is below 0, we want to return 0.0 and turn data.pleaseLand equals false, because we've landed. Else if, oh wait, x. Else if x is bigger or equal to 0 and x is smaller 30, do our logarithm. That was minus 2 times log x plus 1.5. Again, values found tweaking Desmos. And the remaining case is when it's bigger than 30, we will simply return, oh no wait, speed is equal to negative x divided by 10. And lastly, return speed. I think this is much more readable now. If it is below 0, return 0. Set data to false. If it is between 0 and 30, use our logarithm. And if it's above that, our linear function. Okay, let's test this out. No surprises, hopefully, this time. Let's land. Why does it jump here by so much? From minus 3 to 6. I'll have to investigate. But this looks alright, guys. But now I have to figure out, why does it jump here? It shouldn't jump, it intersects. Why does it jump to I think we... might have an issue with our function, but not sure. -2. Logarithm? Of course, the logarithm in Python is actually the logarithm in Python is the logarithm to the base of e, while the standard logarithm in Desmos is to the base of 10, I think. So what we have to do in here is to change the logarithm to ln. And now we see why we have -6 over here and -3 here. Why we jump. A few moments später. Hey guys, welcome back. So I decided to tweak those values behind the scenes because it just ended up taking way too long. So here are the final values. As you can see, I switched out our linear function for another logarithm. Why is that? Well, because if you remember, this was a linear function and it just went to infinity, and the higher up I went with the rocket, the more speed it gathered, and it ended up so fast I just couldn't slow down fast enough. So since this is a landing computer, I decided, well, I'll just use 2 logarithms, and the other one will cap out at, I don't know, maybe 100 meters per second, which is no big deal because I will never actually start to land so far high up. So I would not use this function if I wanted to land from orbit. I will need a different one for that. Okay guys, so here our final flight or landing. Let's go. Up small ship goes. Small ship V3, by the way. It gets bigger and bigger per episode. Only missing some wings. Okay, let's land. Let's also try to steer a little and check if it works as well. Uh-oh, that was too much. But it still seems to work, guys. A little too fast. Oh. Okay, I think you have to trust me that it actually works. So with this double crash, I want to say auf Wiedersehen and thank you for watching.